Good afternoon, everybody. It's 2 o'clock on the dot. We've got a lot to cover today, so we're going to jump right in. We've got to cover the rest of Chapter 4. We left off with Electron Configurations. We still need to cover the periodic trends, and then we get to Chapter 5. So if you don't have a periodic table, look up the one on Blackboard, or you can just Google it, because you'll need one. We're going to start with Electron Configurations, and this again is the end of Chapter 4. We'll start by doing the full electron configuration for iron. But before we do that, I'm going to go through and highlight all the different blocks and kind of label this periodic table. Feel free to do the same thing with me if you have a printed copy or you have a tablet. Everything that's boxed in black is part of the S block. That means that it's filling an S orbital within the S sublevel. Next, we go over to the P block, which is in purple. Here, you're filling all the P orbitals within the P sublevel. Before I get too ahead of myself, those are the different energy levels for each period. And I'm filling in each sublevel. Notice that we don't have a P sublevel until we get to energy level equals 2. Next is the D block. These are all of the transition elements. And they're filling D orbitals. Last but not least, we've got the F block. So you can see where they're supposed to be. These are also called the inner transition metals. So when you go right after barium, you go down to the lanthanide series. And then once you finish with that, you come back up. So this is the F block. You're filling F orbitals here. And for your reference, in each sublevel, so it doesn't matter whether it's 1s or 5s, you have one S orbital. Doesn't matter which P sublevel it is. There are 3 P orbitals, 5 D orbitals, and 7 F orbitals. So if we're looking at the 4p, there are 3 4p orbitals. Each orbital can hold up to 2 electrons. In red, I'm going to write the maximum number of electrons for each sublevel. For the S sublevel, maximum of 2. The P sublevel, maximum of 6. The D is 10. And the F is 14. So this is kind of a whirlwind review of where we left off last time. Now we'll get to the actual question. We need to write the full and the abbreviated electron configurations for iron. We'll start with the full electron configuration. This is iron. It's in the D block. Let me label these. We won't need the F's, so I'll leave them. We need to write the full electron configuration for iron. I'll write that in green. You always start with the lowest energy sublevel, which is 1s. How many electrons can fit in the 1s sublevel? Giving you a hint here. Yeah. We can fit 2. So we'll write that as a superscript. That means that if we stopped here, we would have the configuration for helium. But we don't care about helium. We care about iron. So we need to keep going. We move on to n equals 2, which is the second row. What sublevel am I filling? Sure. What sublevel am I filling next? I'm filling the 2s next. So we're literally just reading each sublevel off the table from left to right. And just like the 1s, it can hold 2 electrons. We're now at a total of 4 electrons. But iron has 26 electrons. So we've got a ways to go. Continuing on in period 2, what sublevel do I fill next? Nope, we're going across the periodic table. So we haven't finished with n equals 2 yet. So we have to fill the 2p. We're literally going across each row. Okay? And in the p sublevel, we can hold a total of 6 electrons. And since this is the p block, look, 1, 2, 3, 4, 5, 6. So we can hold a total of 6. Now we've got a total of 10 electrons. And if we stopped here, we would have the configuration for neon. But we don't care about neon. We care about iron. Now we're in row 3, period 3. What do we fill next? The 3s. How many electrons can we fit in the s sublevel? Two. Then we go across, because we're still in the n equals 3. We have to fill the next energy, the next highest energy in the 3 sublevel, right? So we did S. What's next? The 3p. How many electrons can I fit in the 3p sublevel? 6. So if we stopped here, we'd have argon. But that's not what we want. We need iron, and we're almost there. What do I fill next? The 4s. And we're going to put 2 electrons there. What fills after the 4s? And again, you're just reading along on the periodic table. Yeah, we got to fill the 3d. And that's where iron lives. So we need to count. 1, 2, 3, 4, 5, 6. If you add up all of those little superscripts, it should equal the same number as the number of electrons in the element that you're writing the configuration for. So that's a good check. I highly recommend having a periodic table labeled like this to use along with your homework. And when you take your exam, exam 2, I'd recommend knowing this well enough to recreate it during the exam setting. Now we need to write the abbreviated electron configuration. I need to make a little bit of room for myself here. So I'm going to rewrite this. Now let's write the abbreviated configuration. The abbreviated configuration, which is also known as the noble gas configuration, you use a noble gas to represent all of the core electrons. Iron is in period 4. So we can use a noble gas to indicate everything in n equals 3 all the way back. Yes, that is exactly it. But I'm keep going for those who need a little bit of help. If we want to represent all of the electrons that come before n equals 4, we need to use a noble gas that has that configuration. We're looking at n equals 4. We need the noble gas, which the noble gases are in group 8A, the very last column. You want the n equals 3 noble gas, which is argon. And that contains all of that I just bracketed. 1s2, 2s2, 2p6, 3s2, 3p6. All of that is argon. So instead of writing it all out, we can write argon in brackets, and we know what that means. Then you have to fill the gap between argon and iron. So you write out everything that's in n equals 4 until you get to iron. That's 4s2 and 3d6. So the abbreviated form takes a lot less time to write, but you need to understand the full configuration to understand what the abbreviation really means. I've got another example here, so let me know if you need to talk through this one again, or if you want to go and work through one more example. Okay. So I'm not going to do all of the labeling that I did before because it's kind of time consuming. I will, however, label what we need to write this configuration. And I was just going to do the abbreviated configuration, but I think we should do the full and the abbreviated for barium. So I've labeled each of the sublevels so you can read along. We always start with the 1s. How many electrons can I fit in the 1s sublevel? We can fit 2. By the way, this is what we're going for, barium, with 56 electrons. So we've done 2. What do I fill next? I fill the 2s, and I put another 2. Now we're at 4. What comes after the 2s? Does everybody see that? We fill the 2p after the 2s. Then what do we do? What fills next? Aaron has got this for everybody. So please, if it's like, whoa, slow down, let me know. So let's make sure to keep track with our dots. We fill the 2p, then the 3s. Then we fill the 3p with another 6 electrons. That's 18. Notice that where I stopped, so where our configuration stopped, we have 18 electrons accounted for. The atomic number of the element that we've stopped on the periodic table also has 18 protons and 18 electrons. So that's a good way to check and make sure that your math is right if you're adding things up as you go along. After the 3p, we fill the 4s with 2 electrons. What sublevel do we fill after that? The 3d, okay? We're just going across the table. We did the 4s, then it's the 3d, and there's 10 electrons that we can fit in there. Then we fill the 4p. When you're walking across the periodic table, don't skip. Yeah, don't skip. After the 3d, then we fill the 4p. We just filled in the entire row. If we stopped here, it would be krypton. Notice how each of the noble gases, with the exception of helium because there's only the S sublevel, they all end with a full P sublevel. So it's something P6 is the last thing. Now we're on N equals 5. We fill the 5s with 2, the 4d with 10, and then the 5p with 6. There's the 5s. That's the 4d. And that's the 5p. That would give us xenon. Almost there. How do we complete this configuration? What's the last sublevel that we have to fill? The 6s. 1, 2. Oops. That's the full configuration for barium. I stopped all my counting here. So let's see. 36 would be 4p. So there we go. 56 electrons. That is the full configuration. You see how long that took? For the abbreviated configuration, we can use the noble gas that comes in the period right before barium. So if barium is in N equals 6, what noble gas do I need to use for my abbreviated configuration? The noble gases are in the column that I just put an arrow above. Xenon. So you use the one, if barium is in N equals 6, then you need the N equals 5 noble gas. And what do I have to put after that? Because that's not complete. We have to fill in everything between xenon and barium. So if we were writing our configuration starting here, what would be the next thing that we would write? Yes. (6s2). So what xenon takes care of is all of this craziness. That's xenon. Then all you have to do is put what's left between xenon and barium. So does that feel a little bit better for you guys? We don't have more time to go over more of these. Good. But if you do need help, office hours are on Tuesdays. If you can't make office hours, they're 11:30 to 1. Then send me a course message and we can go over some more of these. The last bit of chapter 4 is trends in the periodic table. We've got valence electrons, which we'll talk about a little bit. And valence electrons, actually I'll just write it in the box. Save some space. Yes, it's always going to be posted. The valence electrons are the outermost electrons. And those electrons live in the outermost main energy level. In our last configuration for barium, this was our configuration, the abbreviated configuration. The electrons in the 6s2 would be the valence electrons. The configuration of those valence electrons would be 6s2. Another way that you can identify valence electrons, they're always going to be in the S and the P. And those are going to be the ones outside of the noble gas core. So that's what valence electrons are. You can figure out how many valence electrons there are by looking at the group number. But it's got to be the one that has the A after it. So group 1A, group 3A. The number before the A tells you, okay, it's got 1 valence electron or 3 valence electrons. Okay. So that's valence electrons in a nutshell. The other 3 trends you can read in the table. We've got atomic size, ionization energy, and metallic character. Atomic size, we're talking about how big the atom is, obviously. Ionization energy, we're talking about the energy required to remove an electron. And metallic character also describes this. How easily does the element lose its valence electrons? I go into detail about these things in the video, so just make sure that you fill in the gaps that I'm not putting in here. What I did do for you is, instead of reading through all these, I made you a little cheat sheet. So if you want to print this out, or if you want to copy this down in your notebook later on, you can. But this summarizes the 3 trends that you need to know on the periodic table. What I'll add to this is that these numbers, the 2A, the 1A, the 2A, all the ones that have the A, those tell you the number of valence electrons. So this one sheet summarizes all of those trends. You'll need to be able to answer questions about, okay, which element of these 3 has the highest ionization energy or the smallest atomic radius. Those are the types of questions you'll need to answer. Is everybody clear on kind of what you're going to be responsible for? And if you're writing notes down, that's okay. Just let me know you're still with me. And let me know when you're ready to move on. Okay. Lewis symbols. This is related to valence electrons. Lewis symbols represent the valence electrons for an element. I went over this in the video, but I want to make sure that everybody gets it, and then we'll do an example together. So I'll have my generic symbol for my element symbol. If I have anywhere from 1 to 4 valence electrons, I just place it on a side. So that's an element with 4 valence electrons. If you have 5 to 8, which you can never have more than 8, then you go back around and you fill them in. You never pair up electrons unless you have to. An example would be boron. The symbol for boron is a B. It's a group 3A element. How many valence electrons does boron have? The group number tells you. Yeah. So, whenever you have that group number with the A after it, the number tells you how many valence electrons. So we have to place 3 electrons. 1, 2, 3. You could also write 1, 2, 3. Or, doesn't matter. As long as you have one side open. So if you did this, that would be wrong. Are we ready to try an example? Because I have a problem for you guys to try. You need to write the electron dot symbol, which is the same thing as a Lewis symbol, for nitrogen. And I already tell you, it's a group 5A element. I'll give you a minute, and then I'll check back in. How many valence electrons does nitrogen have? Right. 5 valence electrons. For our Lewis symbol, start by filling in all 4 sides, and then it's your choice as to where you put that 5th one. So there's one example. There's another. As long as you have 5 electrons total and only 1 pair of electrons, then it is a correct Lewis structure. Questions on this? So there's a little bit more of chapter 4 that we didn't 100% cover in terms of valence electrons and the valence electron configuration. I pointed it out a little bit, but make sure that you understand that as well, because that will be part of your chapter 4 homework. But if you understand configurations and what valence electrons are, then it's not going to be hard to put those two concepts together. With that said, we're about to start chapter 5, which is on nuclear chemistry. Let's get started. Before we get there, we got to review, because I know people forget. Sometimes I do. So, let's review mass number, atomic number, and all that jazz. I've got magnesium 26. I'll give you a minute. I want to know how many protons, how many neutrons, and how many electrons are in a neutral atom of magnesium 26. So for the sake of time, I'm going to get started here. We've got magnesium 26, which is an isotope of magnesium. That means it's got the same number of protons, different number of neutrons, right? You figure out the number of protons by looking at the periodic table. The atomic number is the number that is above the symbol for magnesium. That number is 12. In a neutral atom, you have the same number of protons as you do electrons. That's easy. But what about the neutrons? We're given this hint. This 26 is the mass number. The mass number is the total number of particles in the nucleus, which means we're adding together the number of protons plus the number of neutrons. So if we know that the mass number is equal to 26, and that out of that 26, 12 of those things are protons, that leaves 14 neutrons. So I'll write it as kind of an equation up here. Our mass number was 26, 12 plus the neutrons. And that's how we got here. So we've got 14 neutrons. You will need to remember this concept for chapter 5. The idea of what a mass number is, that is the protons plus the neutrons. Everybody shake the cobwebs off a little bit. We ready to go? So radioactivity, sometimes that sounds like a scary word. It's not. It's natural. It's all around us. So it comes from an unstable nucleus. When the forces within the nucleus can't offset the repulsions between the protons, you're going to release some energy. What that means is you may actually release pure energy, or you might release small particles of energy. Either way, that's what radiation is. And in doing so, that nucleus becomes more stable. The forms of radiation that we'll talk about are below. We've got alpha and beta particles, positrons, pure energy. A radioisotope is an isotope of an element that emits radiation. we always have the mass number as part of the name. The example here for the atomic symbol is for iodine 131, and it's used a lot to diagnose and treat thyroid disorders. Iodine 131 has a mass number of 131. If you look at the periodic table for iodine, the atomic number is 53. How many neutrons are in this isotope? This is practice, y'all. How many? Yes. You have to take the 131, which is the mass number, and subtract the number of protons, which is 53. So when you see a symbol like this, you need to recognize the mass number is at the top, the atomic number is at the bottom. You'll never see a mass number on a periodic table. It's always the atomic number at the top. That's what you want. This chart, I would recommend reproducing it and putting it in your notebook, or printing it out and putting it in, or something like that. It's got forms of radiation, their symbols, and then the mass number and charge associated with it. We're going to be doing some examples of balancing nuclear equations, and for your exam, you need to recognize all of these symbols. It will not be spelled out to you that an alpha particle is a helium atom with a mass number of 4 and a charge of 2. It's not going to be spelled out. So make sure that you memorize. Everybody good on that? Let's talk about some properties of radiation. We're going to cover alpha and beta particles and gamma rays. In general, what we're talking about here is if you're just sitting there and a source of alpha particles, beta particles, and gamma rays were to suddenly appear, with alpha particles, you'd be okay. Okay. Shielding that you need, pretty much you're wearing clothes, so you're good. Doesn't travel very far through tissue, doesn't travel very far through air. Beta particles, heavy clothing. So if you're wearing a lab coat, or if it's maybe colder in your room or wherever you are and you're wearing a jacket, you'd be okay. It travels much further in air than the alpha particles. A little bit further in terms of tissue depth, but it's not really getting in very far, not going to do as much damage. Gamma rays, however, they can literally go straight through you. They travel very far in air, 500 meters. We're talking about 500 meters versus a few hundred centimeters, okay? So 2 to 3 meters. Versus 500 meters. Big difference. Those gamma rays can go straight through you, so you need shielding that is very thick, like concrete, or lead, something very dense. You'll need to know the difference, not necessarily the exact numbers, but the fact that alpha particles don't travel as far, gamma rays travel the farthest, and the types of shielding you need for each particle type. Does that make sense? You know what you're going to be responsible for? Let me know when you're ready to move on. So let's summarize the types of radiation. We're going to go over these two types, and then we'll do a practice on balancing nuclear equations. The first type we'll cover is an alpha emitter. That means that it's something that emits an alpha particle. The products are an alpha particle and a new element. That new element is going to have a mass number that is 4 less than the original alpha emitter and 2 less for the atomic number. Remember that this is an equation. So the mass number on the reactant side, this isn't exactly a reactant per se in the mixing chemicals together sense, but you may be more familiar with that terminology. Whatever the mass number is on that side has to equal the sum of the mass numbers on the product side. The same thing is true for the atomic number. So if I were to give you a problem that said a particular element was an alpha emitter, and I asked you for what the new element was, you would have to supply this information so that you could actually balance the equation. That's why I am imploring you to know these symbols, know their names, and know the symbols. The second reaction type we'll talk about is the beta emitter. Here you're losing a beta particle. A beta particle is essentially a high energy electron. You release this high energy electron and you create a new element. The mass number will be the same. So the number of protons and neutrons will be the same. But your atomic number will increase by 1. I'll show you what that looks like. Can I show you an example? I'm trying to be mindful that you might be trying to take notes. So let me know when I can show you an example of how to balance one of these equations. Okay. Let's go. Write the balanced nuclear equation for the beta decay of cobalt 60. Let's break this down. Beta decay. That means loss of a beta particle. The symbol for a beta particle is that. Cobalt 60. That means that 60 is the mass number. We don't know what the atomic number is. Where can we find the atomic number for an element? The periodic table. You're giving me more information than I'm asking for. But yeah, you look at the periodic table. And when you do that, you find that cobalt has an atomic number of 27. Yeah, you're doing too much work. So these are the pieces of information that we're starting with. We're losing a beta particle because it says beta decay. Cobalt 60, we know the mass number is 60, and we can look up the atomic number. We can start writing our equation. We know that we release a beta particle, and we make some new element. On the previous slide, what we said for beta decay, which another way to say that is a beta emitter. They're all different ways to say the same thing. For the new element, the mass number remains the same. The atomic number increases by 1. So we know that our new element is going to have a mass number of 60. If we have to increase the atomic number, well, we're starting with 27. We have to add 1. That's 28. So that's our new atomic number. This atomic number is what you use to figure out the identity of the element. So you look up 28 for the atomic number on the periodic table. Let me know what element that is. It's nickel. So the balanced nuclear equation we have our cobalt 60. It releases that beta particle, and we've got a new element, nickel. Just so you can see where it's from. This is our complete answer. I've got another one that's kind of similar after we talk about a couple of other problems, or another couple of radiation sources. How does this feel for everybody? It'll take some practice. I know I posted the chapter 5 video late. I apologize for that. But if you watch the video and then come back around and try to do these examples fresh, I think it'll make some more sense. So let's go forward. We'll talk about another couple of reaction types, and then we'll do another similar type of problem. So I talked about positron and gamma emitters a little bit in the video, but I didn't do an example of a positron emitter. A positron is like a positive high energy electron, or like an anti-electron. And what I mean by that is that instead of having a -1 as a sign, it's +1. So that's a positron. The name sounds like super futuristic or something from a movie, you know, or it makes me think of like Transformers, Positron. Like it's, you know, like some little Mazda car or something that transforms into a robot. That's just my brain. Hopefully you don't have my brain. It's a little crazy. Anyway, we'll do an example of that as balancing a nuclear equation. The other kind of radiation that we're not going to go over because it's pretty simple is the gamma emitter. So for the gamma emitter, all you have to do is write this symbol for gamma rays. And then you have a stable nucleus of the same element. So the mass number is the same, the atomic number is the same. It's not a new element. All you did was release energy. So now I'm going to go ahead and show you an example of a positron emitter. We've got magnesium 23. It's a positron emitter, and we've got to write a balanced nuclear equation for its decay. Positron emitter tells us what the particle is that we're losing. And at this point in time, you're not watching so that you can make sure you can replicate this exact problem, but understand the flow of how to solve a problem like this. That's why I show you example problems. Magnesium 23 is what we're starting with. The 23 is the mass number. You'll always be told what the mass number is for the starting material. In this case, it's magnesium. What's the atomic number of magnesium? Look it up on your periodic table. No, that's not the... Yeah, it's 12. 25 is about the atomic mass of magnesium. So that atomic number, you always fill in from the periodic table. Don't freak out because you don't have that information. Let's write out our equation and figure out what it is we need to fill in. For a positron emitter, you're going to make a new element in addition to releasing a positron. For this new element, the mass number stays the same. The atomic number that is going to decrease by 1. So these rules over here, that's something that you will need to memorize. So the chart that I was showing you, it's actually one slide, but I broke it up into 2 so we could cover it and it's a little bit less intimidating. But understand, okay, this is a positron emitter. That means I make a new element, the mass number is the same, the atomic number decreases by 1. That's the information you need to know cold. Then you can go to your periodic table and you can figure this all out. The mass number stays the same, then that means it's going to be 23. If my atomic number decreases by 1, my atomic number for magnesium is 12. I subtract 1, that's 11. What element do I have? It's sodium. And we know that because of the atomic number. So the balanced nuclear equation is here. And again, this information you need to memorize. That's the key to being able to solve all these problems. If you practice doing them, then you'll recognize all the terminology and it'll kind of instantly come to your brain. Okay, positron, that means this is what my reaction looks like. This is what the new element, this is how I find the new element. So even if it doesn't 100% make sense to you, do you understand the information that you need to memorize in order to do these problems? Let me know when you're ready to move on. We're still going to be doing some of this balancing as we move forward. We've got another example. It'll just be a different problem type. So don't worry if you're like, man, I don't know if I'm ready. We have some more. So we can produce radioactive isotopes. You can take a stable nucleus that's all happy and fine on its own, and then bam, you hit it with something, small particle. Then you make a new radioactive nucleus, and you might release some energy or make another particle. Okay. That process is called transmutation. The example shown is you have a stable nucleus of boron. Okay, it's non-radioactive boron. And you bombard it with an alpha particle. Then you form a new radioactive nucleus, which is now nitrogen, and you also release a proton. So this process is called transmutation. I feel like it's kind of aggressive because I envision, a non-radioactive atom of an element just hanging out, doing what it likes to do. And then all of a sudden there's just a sneak attack. Somebody just comes and throws a snowball at you. Like, I didn't know I was in the snowball fight. Why are you involving me? I was making a snow angel, being peaceful, enjoying the elements. And then you just come at me sideways and hit me in the back of the head. That's what I think of when I think of transmutation. If that really strange example of someone hitting you with a snowball in the back of the head helps you remember what that is, good for you. We can write balanced nuclear equations based on the information that we're given in a problem to show what transmutation has occurred. We've got a radioactive isotope that is produced when you have a neutron that bombards technetium-98. We're given some information about what happens in the process. We start here with this element and we release an alpha particle. So for our reactant side, we know that we're starting with this element. The 43 is the atomic number, which you can find on the periodic table. But here, most of the equation is already filled in. We just need to figure out what radioactive isotope did we make. This is just a balancing game. We've got to figure out the total mass number on both sides. The mass number is at the top. (98) is from our element, and we have a 1 from the neutron. So our total mass number for the, we'll call it reactant side, is 99. We'll do the same thing for the atomic number. We've got 43, and the neutron doesn't have anything, but I want to show you and remind you that you're summing all of the atomic numbers on that left-hand side. And I'm a color coding person, so I like to see where things come from. So we've got our totals for the reactant side. We need to do the same thing for the product side. And this is how we can figure out what our new element is. The total mass number on the reactant side is 99. Has to be the same thing on the product side. And that total is going to be the mass number of our new element, which we don't know, plus 4 from the hydrogen, or from the helium, excuse me. What's the mass number of our new element? If we know the total mass number for that side is 99, and the mass number of helium is 4, what is the mass number of our new element? So that's the new mass number. Now we've got to do the same thing for the atomic number. And feel free to work ahead of me. You can put in the chat what you think the atomic number is going to be for the new element. We know the total atomic number has to be 43. We're not just pulling stuff out of thin air. The atomic number for helium is 2. That means that our new atomic number for this new element is going to be 41. What element is this? Yes. That is the new radioactive isotope. What I want you to see that's constant with all of these balancing questions is that the mass number and the atomic number on one side of the equation, if you total both of those up, it'll always be the same on the other side. That's how you can learn what the new element is. Questions here? You can let me know if you have a question, or you can tell me, let's just move on. Let me know how you're feeling about it. All those things. We still writing? Watching Netflix? Let me know you're still with me. All right, thank you. Do we need a 5-minute break? That's probably about all we can do this class. Then let's take 5. All right, be back at 3:30. So let's get back to it. I know we're moving kind of fast, and sometimes it's just like, woo. If you feel like that, you can just let me know. And you can just say, I'm with you, but I ain't with you. I get it. I still have to cover the material. We still got to try to get through it all. But I at least know you're there. And you may just need a minute. You may just need to go back to it or say, okay, I'm going to take 5. I know we ain't officially on break, but I need to give myself 5 so I can just breathe. That's totally fine. I get it. So we left off, we're about to start talking about radiation measurements. We really care about this because there have been some issues with nuclear power plants and things like that where there have been, kind of disasters. And these areas are still very, very, very radioactive. And you can measure how much radiation a person has absorbed in their body. You can measure the activity, which would be if you're trying to do some kind of experiment and you're using a radioactive isotope. Measuring the activity would tell you how much of that isotope you have. So radiation measurements are very important. The SI unit for radiation measurement is the sievert. Oftentimes, though, you'll see rems or millirems. What you see here are equalities. I would put this table in your notebook. These are the relationships that you're going to need to know. They'll be supplied for you on the exam, but you'll want to reference these when you're doing homework. What I want to do is take some time to do some practice problems using all of these different measurements. So I'll do a problem, show you how to do it, and then I'll have you do a very similar problem. Let's say that we have a sample of technetium, and it has an activity of 1.5 curies, which the Curie is named for Marie Curie, who did a lot of work with radioactivity. She didn't get the Nobel Prize until, way after she died. Someone else took the credit for that because in those days, women didn't get credit for the work that they did. Had to be a guy. But I digress. How many disintegrations occur in the technetium-99 sample in 5 seconds? Now, these problems are problems that you might see on an exam. So even if you're not doing them along with me, make sure that you go back and look at the notes or watch the video or both, because I'm giving you the keys to the kingdom here. I've literally pulled questions that are very much like test questions to help you practice. The information that we care about from this problem: we know that this sample has activity of 1.5 curies. We want to know about how many disintegrations occur in 5 seconds. What disintegrations is, that's just the number of atoms that have decayed. And we want to know how many of those atoms decayed in 5 seconds. No, I wrote it like that. So this is the question we have to answer. We'll need to use one of our equalities. This is why the table is so important. 1 curie is the same thing as 3.7 times 10 to the 10 becquerel. One becquerel is the same thing as saying 1 disintegration per second. So what we can really say with that information is that 1 curie is equal to 3.7 times 10 to the 10 disintegrations per second. This is the equality that we want to use because we're trying to convert from curies to the number of disintegrations that occur in 5 seconds. Using our information from the problem, we're starting with 1.5 curies. we need to write a conversion factor that's going to take Curies and make them into disintegrations per second. And excuse me, this should be disintegration. Jumping a little bit ahead of myself here. So if we know that we can go from Curies to disintegrations, like this, then we can figure out how many disintegrations that is. We multiply that by 5 seconds because that's how many seconds this is taking place over. So each second, we've got 3.7 times 10 to the 10 times 1.5 disintegrations going on. That's your calculator answer. But we need to look at sig figs. The activity has 2 sig figs. The time has 2 sig figs. So we should also have 2 sig figs. So these are really conversion problems. Let's go through another one. If I can move to the next slide, let me know. So I know you might be writing things down. Because y'all aren't so responsive today, I'm taking it that this is kind of a lot. This is still the material we have to cover. But if you want me to just kind of go through and show you, let me know. I won't ask you as many questions. I'll just kind of go through. So let me know if that would be more the vibe today. That you just kind of want to absorb. And then we can maybe do a few questions next week. Okay. So I think what makes the most sense is we'll finish up. Probably watching the video will help too. And then come to office hours next week or set up an appointment with me. I want you to have a little time to kind of work with the material, do a little bit of practice, and then figure out where you're having issues, because in office hours we can't just reteach the whole lesson. So I need you to do the work of figuring out, okay, I got lost here. This part doesn't make sense to me. And then we can kind of go at it again. Now next week we're going to be covering chapter 6, which is a very big chapter. So we won't have all the time in the world to go back over chapter 5. But I will, to the best of my ability, throw in one or two kind of do now problems that cover some of the more confusing topics. So I'll work through another problem just so that you can see it, and maybe it'll kind of make a little bit more sense when you have time to wrestle with it on your own. So it's the same exact problem, but we've got different activity. We've got an activity of 0.5 curies. And we want to know how many disintegrations occur in that time. That's an equality that we know from our table. It's not 1, it's 3.7 times 10 to the 10. And we know that 1 becquerel is the same as 1 disintegration per second. So I'm going to show you a little bit of a different way, and that might make a little bit more sense to you. We take our activity, and we first want to write a conversion factor to go from curies to becquerel. We want to get rid of curies, so that should go on the bottom. Becquerels go on the top. Then we can take becquerels and convert that to disintegrations per second. The last part of this is taking that number and multiplying by 5 seconds. We can cancel our units. So we first convert to becquerel. Then we get rid of becquerel and swap that out for disintegrations per second. We get rid of the seconds, and we're left with just disintegrations. When you do all that math, you're taking 0.5 times 3.7 times 10 to the 10. You're multiplying and dividing by 1, so you don't have to put that into your calculator. And then multiplying by 5. When you put all that in, you get this number. That's your calculator answer. But again, we have to worry about sig figs. We've only got one sig fig in our activity. So we've got to report with one sig fig. Again, this is a conversion problem. Let me know if I should stay on this slide if you're copying something down. Okay. Yeah, sometimes you need to see it a couple of times. So I'll show you two examples of another problem type, and then we'll move on. This is still just another conversion problem. It just has to do with radiation. The recommended dosage of iodine 131 for a test is 4.2 microcuries per kilogram of body weight. How many millicuries should be given to a 55 kilogram patient? And we're told that 1 millicurie is equal to 1,000 microcuries. .2 microcuries per kilogram. That's a conversion factor. We can use it to figure out the dosage or the weight. In this case, we need to figure out the dosage. How many millicuries? And don't get confused with micro and milli. The dosage is 4.2 microcuries for every 1 kilogram of body weight. That's our conversion factor. We need to go from that to the number of millicuries. The patient's weight is 55 kilograms. We get that from the problem. We use our conversion factor to go from kilograms of body weight to microcuries. But the question is asking for millicuries. And we're told 1 millicurie is equal to 1,000 microcuries. That's our second equality that we can use to write a conversion factor. If we want to get rid of microcuries, we've got to put 1,000 microcuries in the denominator so it will cancel out, and 1 millicurie in the numerator. With our first conversion factor, we get the number of microcuries. With our second conversion factor, we get millicuries. When you type this into your calculator, you're doing 55 times 4.2 divided by 1,000. You should get from your calculator 0.231, something like that. But we always need to account for sig figs. Our weight has 2 sig figs, and the conversion factor we're given has 2 sig figs. So that's how we write 2 sig figs for that. This one might be a little bit easier to understand. So let me know if the dosage question is okay. Or if it's not. I just want to know. I've got another one, so. For the sake of time, I'm going to press forward, but I understand that this is kind of a lot. So please do reach out to me because you're going to have homework due next week for this, and I don't want you just struggling through it. Same problem, only this time we've got a patient that's 75.6 kilograms. We start with the patient's weight. And we get to the dosage in microcuries. Then we convert microcuries to millicuries. And that's using the equality that we were given, 1 millicurie equals 1,000 microcuries. And we write a conversion factor. Microcuries go on the bottom to cancel out, which would leave millicuries. Always do the unit analysis. In your calculator, you'd type 75.6 times 4.25 divided by 1,000. When you do that, you'll get 0.321, and that's millicuries. This time we've got 3 sig figs for the dosage and 3 sig figs for the mass. So we're done. I'll let it sink in a little bit. The next topic we're going to do is the half-life. Half-lives may or may not be something you've encountered already, but we're just talking about the amount of time that it takes for the radiation level to decrease to half of its original value. So if I start with 20 milligrams of a radioactive isotope and its half-life is 8 days, well, in 8 days, I'm going to have 10 milligrams left of that radioisotope. If I wait an additional 8 days for a total of 16 days, that's 2 half-lives, and I now have 5 milligrams. Let me know if this concept makes sense to you about half-lives. Baby Hefner has arrived, so I'm going to pause for about 2 or 3 minutes to get him squared away. All right, so you had an extra minute or two to let things kind of shake down. Again, I know that this is a lot. We finished one chapter. We about to finish another chapter. So please reach out. This is around the time of the semester in this class where people kind of start to worry. And I would encourage you to, instead of worrying, reach out. Use Upswing if you can. Get some help. Talk to other people who have taken the course. Come to office hours. Study together. Maybe there's something that you understand that a friend of yours doesn't, and y'all can teach each other. All of those things will help. And I'm here to help you. So please let me know how I can be of service, and I will try to accommodate you all. With that, I'm going to continue to just steamroll through this lecture. It hurts my heart to know that I have to keep going without just taking all the time in the world. But we don't have all the time in the world. I've got 27 minutes left to complete everything. And that's not a lot of time. So I'll show you another practice problem for how to solve half-life problems. Or half-life problems, not half-live. Carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old, and the half-life of carbon-14 is 5,730 years, what fraction of this half-life has passed? What we're told in the problem is that one half-life is equal to 5,730 years. That's an equality. From an equality, we can always write conversion factors. I'll abbreviate half-life HL. Those are the two conversion factors that we can write. Now we need to take the amount of time that has passed, which we're told is 2,000 years, and use one of these conversion factors to figure out what fraction of a half-life has passed. We're trying to get rid of years. So years should be on the bottom of whichever of these conversion factors we use. When you do this in your calculator, you're doing 2,000 divided by 5730. You'll get a decimal. So that is the amount of time. Now, if we're doing sig figs, there's only one sig fig in 2,000 years. So our fraction would be 0.3. And that's it. A lot of these questions, you're given the information to write an equality. You write that equality, and then you use a conversion factor to get from the units you have to the units you need. I'll show you another example. We've got the half-life of iodine 123 is 13 hours. How much of a 64 milligram sample is left after 26 hours? The 26 hours, that's the amount of time that has elapsed. 13 hours is the half-life. We can write an equality for the half-life. And from there, conversion factors. We can use this to figure out how many half-lives have passed. 26 hours have elapsed. We use our conversion factor that has hours in the bottom so we can figure out the number of half-lives. 26 divided by 13 is 2. That's not the question. The question is how much of our 64 milligram sample is left. After one half-life, you divide by 2, and you get 32 milligrams. For the second half-life, you divide by 2 again, and that gives you 16 milligrams. That's our answer. I'm going to pause here. Does half-lives make any sense at all? If it doesn't, let me know, because that will inform how I help you next week. So if you're lost, you can just tell me you're going to have to reteach everything, which I can't do. But if that kind of makes sense, let me know. So thank you. There are lots of medical applications for radioisotopes. And when choosing a radioisotope to use in nuclear medicine, which is what it's called, you want something with a short half-life. Radioisotopes, remember, their nuclei are not stable. They're releasing energy, they're releasing particles, and they're interacting with all of the other things in your body. So you don't want loose energy and loose neutrons and, alpha particles and things interacting with your proteins, your DNA, RNA, and all the important molecules in the cell. Your cells do not differentiate between non-radioactive atoms and radioactive atoms. So they will incorporate whichever one is available. Once they're incorporated, those radioactive atoms are detected because they can emit radiation. That's what they do. That's how you get an image of an organ. And as long as you use a radioisotope with a short half-life, you'll have decay of that radioisotope within a few months. So the key that you need to remember here is that radioisotopes with short half-lives are used in nuclear medicine. So which of these are most likely to be used in nuclear medicine? We've got potassium-40 with a half-life of like 1 billion years, literally. Potassium-42 that has a half-life of 12 hours. And iodine-131, which has a half-life of 8 days. Well, I'll tell you what, 1 billion years, that's a no. That's way too long of a half-life. But 12 hours and 8 days, those are pretty short. So those are likely to be used. The last set of topics, we're going to talk about fission and fusion. Nuclear fission is taking, say, uranium, for example, and you bombard it with a particle, a neutron in this case. You then form an unstable nucleus. It will decay and create 2 new elements plus a lot of energy. That's what this little sunburst is. That's a lot of energy. And it also makes more neutrons. Those 3 neutrons can then go on to find 2 more or 3 more uranium atoms to do the same thing again. This is called a chain reaction. This kind of fission reaction is what's used to generate power. So here in North Carolina, we've got, I think, a couple of nuclear power plants. I know one for sure is in Charlotte. I believe there's another one as well. So that's the reaction that's going on to generate energy. It creates a lot of energy when you create those new elements and release neutrons. So that's fission. You're doing a bombardment, creating an unstable nucleus. It releases energy, new elements, and neutrons, which then go on to fuel more and more reactions. The other reaction type is nuclear fusion. Yeah, so there's actually a another slide that's in the lecture notes from the YouTube video that's already posted. And it has kind of more of a propagation of this nuclear fission reaction. So if you're the type that likes to write it down, you can go to that one, or you can just kind of print it out. But I'm telling you what you need to know for what nuclear fission is, so you can compare it to nuclear fusion. Nuclear fusion is what happens in stars. So our sun, which is a really big star, and all the other stars in the solar system, they all use what's called nuclear fusion. And what happens is you have different isotopes of hydrogen. Notice that these mass numbers are different. Those hydrogen isotopes combine in a fusion reaction and you generate helium. You also produce a neutron and lots of energy. That energy is what reaches us here on Earth. So if you can imagine, the sun is like, I don't even know how many light years away, but it's doing this nuclear fusion reaction and it's releasing so much energy that it's reaching us all the way down here on Earth, warming us up, providing energy for plants to grow, and all the things. So this nuclear fusion reaction is literally the key to life being sustained on Earth. Kind of a wow moment for me. You'll need to be able to differentiate between nuclear fission and nuclear fusion. So know what these two reactions are and be able to kind of describe it and know when you're talking about one versus the other, like with this learning check. So I'll do a couple of these for you just so you get a feel for it. You have to indicate whether each of these is describing nuclear fission or fusion. In A, we've got a nucleus splits. A nucleus splitting means fission. Fusion, you can think of like a fusion restaurant, like a Asian fusion restaurant, right? You're blending things together, you're mixing things together. So that's not going to be a split. It's got to be fission. And in that reaction, you've got uranium being bombarded and then eventually splitting into two different elements and some neutrons and releasing a bunch of energy. Large amounts of energy are released. That's both. Small nuclei form larger nuclei. Fusion, we're bringing things together. So this is the kind of question you'll need to be able to answer. You can fill in the other two, D and E, as practice for yourself, just so you can reassure yourself that you get the concept. We've got one more of these kind of balancing type questions that I'll go through for you, and hopefully that will help when you're going over this again to reinforce how to do these nuclear equations. So this is a different fission reaction. It's still involving uranium. It's being bombarded by a neutron. We're forming this element and another one that we have to figure out. We're also releasing two neutrons and a lot of energy. We've got to figure out the total mass number on this side. So we're going to take the 1 from the neutron plus the 235 from uranium for 236. We do the same thing for the atomic number. The neutron, it's a neutron, so it doesn't have any protons. But uranium does. So that's where those numbers come from. On the other side, we know that everything has to equal 236. With our one element that we know we form, we've got 137 for the mass number. We also release 2 neutrons. And they each have a mass number of 1. And then we have a question mark for our new element. We have to do the same thing for the atomic number. We know it equals 92. We've got 52 from the element that we already know is formed. And then we know we've got this mystery element that we form. So that's where we get those numbers. When we solve, we've just got to do a little bit of addition and subtraction. This question mark, you'll find it's 97. And this question mark, when you solve it, will be 40. And baby Hefner is just trying to be loud for no reason. But that's okay. Maybe he'll bring you some joy. So remember, it's just solving an equation. So you're solving for x in both of these. The atomic number tells you the identity of the element. Zirconium has an atomic number of 40. So that's what the identity of the other element is. So this question type is really a bombardment, right? Or transmutation. And we did one of those earlier. And I'm sure that you've been holding your breath waiting for this slide, because that means it's over. The homework for this is due Wednesday of next week. Do not wait to start it. If you need help, reach out, let me know. My office hours are on Tuesday from 11:30 to 1. Otherwise, it's by appointment. So Wednesdays and then Thursday morning are usually the time that I leave for student individual appointments. If that works better for you because you just can't make Tuesday, or you want a one-on-one, I do 30-minute sessions. So please use course messages to sign up for that. Exam 2, I just want to get it on your schedule here. It'll open March 18th, and it covers chapters 4 through 6. So again, don't delay. Come to me with your questions, your concerns. Let me ease your mind and help you understand the material. The other thing I'll throw out there is remember that March 15th, it's on the syllabus. March 15th, midterm grades are due. So you'll see those, within a couple of days of them being submitted. I'm going to be submitting mine about the 13th, 14th. So everything that we've done will be included in that grade. There were some issues with mastering chemistry for some of my classes. I don't think the same issue has happened, but people were working on things over this past weekend, and the Pearson site has some issues. I think they were performing some maintenance. So I'm going to go through and make sure that everything is up to date. I'll update your mastering chemistry after you complete the Chapter 4 stuff. Chapter 5 probably won't be, yeah, it'll be included. So Chapter 4 and Chapter 5 mastering chemistry homework and quiz will be included in your midterm grade, along with exam 1. So make sure you got all that stuff turned in. If you don't have any questions, you're free to go. Otherwise, you can stay and talk for a while.